So first of all, well, Happy New Year to everyone. In the name of the International Solvay Institute, it's my great pleasure to welcome you to the second lecture of the 2020 New Horizons Solvay Lectures in Physics, given by Professor Douglas Stanford from Stanford University. So let me briefly recall that the object of the New Horizons Solvay Lectures program is to invite a brilliant young scientist with already high visibility and well-established stature to give a series of lectures on the field of his work and to interact with research teams and in particular with young researchers from various Belgian universities. Now, the 2020 edition is the third edition of the program, which started in 2018. The previous lecturers were Zohar Komagorski in 2018 and Alexandra Walczak in 2019. Now, for 2020, because of the pandemic, the program has been unfortunately strongly disturbed since the lectures have been and will be given exclusively online. For that reason, direct interactions will be less than usual, but this was unavoidable. And the last lecture will be given the day after tomorrow on the 20th, again at 4 p.m. We are very lucky that Douglas accepted our invitation. Douglas has made seminal contributions to understanding quantum properties of black holes, and in particular, the role of wormholes in connection with the information paradox, which is the main subject of his lectures. I wish to thank Frank Ferrari, who has been instrumental in the invitation of Douglas and in setting up the program for 2020. Since I will have to leave earlier, Frank will chair this session as well as the one on Thursday. So Frank, you now have the floor and we can start. I think Frank is there, I hope.
Yes, I'm here.
Okay, good. So you have the floor. So thank you.
Go ahead, Douglas. And so, we're very impatient since the first lecture was delivered in June. So.
Okay, yeah. Well, thank you for the introduction and thanks for the opportunity to speak here. The only thing I want to add is that my impression of what these lectures were sort of supposed to be like is an informal thing where I would be traveling from maybe one Belgian university to another over the course of a few days, and we would have sort of a small seminar with a lot of interaction. And that sounds really fun, and it's a shame that we don't get to do it that way, but we can try to approximate it by keeping this presentation informal. And I would really like to encourage all of you to interrupt and ask questions. Let's just pretend that we're having this more informal interaction, and it will be better for all of us, certainly more fun for me. Okay, and I think in the first lecture in June, we managed to approximate that pretty well. So I think that you guys are perfectly capable of jumping in whenever you want. So since it has been over 6 months, I want to start by just briefly reviewing what happened in the first lecture. So let's discuss that. So the lectures are about space-time wormholes, and in the first one we started by defining what a space-time wormhole is, following the definition in the paper by these folks here. And so what it is, according to them, it's a extrema of the action, or a classical solution of Euclidean quantum gravity, that is, of Einstein's theory of gravity in Euclidean space-time signature. And it's a solution that connects together two asymptotic regions, or arbitrarily separated regions of points of the same geometry. So you could have in mind something connecting together two different asymptotic regions like this, a wormhole kind of like that. Or you could have in mind something connecting together two very distant points of the same space-time. So with just one asymptotic infinity, you could imagine a wormhole that's connecting together two different points. And this drawing on the right is a little bit misleading because it makes it look like the wormhole has to be itself very long in order to connect those together. But what you can do is you can redraw this figure in a way that makes it clear that it doesn't have to be long. We can redraw this kind of flat part like this. And then we can draw the wormhole connecting together widely separated points on the kind of two folds of this flat spacetime. So that's what a spacetime wormhole is, or a Euclidean wormhole. Either of these things. So last time we discussed some puzzles that have come up over the years in thinking about these kinds of solutions, these kinds of objects in gravity, and we discussed three of them. So the first one is what was called loss of coherence. This is something that people worried about in the early days of these wormholes. Giddings and Strominger, Lavrelashvili, Tinyakov, Rubakov, and Hawking worried about this. And we discussed a kind of resolution of this, which is closely connected to the replica wormhole discussion of black hole evaporation. A second puzzle is the fact that wormholes connecting together very distant points, like this one up here, they can lead to correlations between very distant parts of the universe, and it's a violation of that constitutes a violation of cluster decomposition, or the fact that correlations should decay at very long separation. It's a type of non-locality, a type of non-local correlation. And this is something that was discussed by Coleman, and there's a kind of partial resolution of this, which was the interpretation by Coleman that these wormholes kind of represent an average over microscopic couplings in the gravity theory. So it's not so much a resolution as an explanation for the lack of cluster decomposition. So these two puzzles have sort of been more or less understood, I would say. The third puzzle, though, is a topic of a lot of current research and debate, which is another problem which is sort of related to the second one. It's the factorization problem. It's the problem that if you have a wormhole that connects together two asymptotic boundaries in the context of ADS-CFT, or gauge gravity duality, then that implies a correlation between partition functions, which is inconsistent with the fundamental microscopic description of the boundary partition functions as describing a unique quantum system. So somehow there's some tension between the existence of these wormholes and the microscopic description of the boundary theory. And this is something that has been discussed, starting with a paper by Whitney and Yao, Maldacena Maoz, and Arkani Hamed, Orgera, and Polchinski. They've discussed this. It's kind of come back in recent years, and there's a lot of discussion of this point in the literature currently. We're going to return to it on Thursday. So we're going to return to problem 3 on Thursday. So I won't talk more about it now. Okay, so this was a review of the puzzles that we discussed last time. And for the most part, last time we didn't really worry about actually constructing wormhole solutions. We just kind of assumed that something like these drawings above can exist, and we discussed some puzzles that arise if they do exist. But we just started, before we ran out of time, we had just started discussing how you would go about trying to find such solutions, and why it's a little bit difficult. It's not as easy as finding a black hole solution. It's a little bit more difficult to find a wormhole solution like this. So we got as far as this slide. So let me just sort of recap this calculation here, and that will get us ready to start today's lecture. Okay, so here I'm following discussion by these folks, especially a nice recent paper by Muralf and Santos. So let's imagine that we're trying to find a wormhole solution of the first type, one that connects together two different asymptotic regions. So a Euclidean signature solution that connects together two different asymptotic solutions. And to make things easy, let's assume a kind of an ansatz for the wormhole, where we have a very simple solution. Let me actually use a different variable here. This will make it easier later. So we have a rho coordinate that's going along here. And then we have a scale factor, which is a function of rho times some fixed internal geometry. So this isn't the most general thing you can have, but it's going to be enough to make the point that we want to discuss. Let's imagine that we're trying to find such a wormhole solution in the context of ADS-CFT, which is what these authors and to some extent these authors were trying to do. So we have negative cosmological constant, lambda less than 0. Okay. So here's our candidate metric, d rho squared plus a squared of rho d sigma squared. And we can write down the 0,0 component of Einstein's equations, what's sometimes called the Friedman equation. And it takes the following form: a dot over a squared is equal to the right-hand side. So the right-hand side contains the matter density minus rho matter. It contains 1 over LADS squared, that comes from the cosmological constant. And it contains k over a squared, where k is the curvature of the manifold sigma. So let's try to imagine solving this equation. There's kind of a problem that arises when you try to solve this equation. In the case where rho matter equals 0 and k is positive, so this is the case considered by Whitney and Yao. So if we imagine that rho matter is equal to 0 and k is positive, then there's no solution to this equation. And this is kind of the simplest case you might want to consider. So we just consider a boundary which is like a sphere times time in ADS-CFT. This is the most common type of boundary topology that we consider. And rho matter equals 0 just means we're looking for a vacuum solution to Einstein's equations. So this is the first case that you would look for. This is the first case you would study, and you would try to find a simple wormhole solution here. And there is no solution. So how do we prove there's no solution? It's a super simple argument. If we look at this sketch of the wormhole here, then in order for this to have two separate asymptotic regions, the scale factor needs to go to infinity on the left-hand side. A needs to go to infinity over here, and A needs to go to infinity over here. So it's very big on the two sides. And so it has to have some minimum in between. So in between, there should be some minimum, and that's a location where A dot, that is the derivative of A with respect to rho, should be 0. And well, if we try to solve this equation with A dot equals 0, the left-hand side vanishes. Rho matter is 0 by assumption. And here we have two positive terms. If the curvature is positive, then both of these terms are positive. So there's just no solution. And you can rule out the existence of a solution by thinking about this point in the middle. Now, Whitney and Yao upgraded this argument to a theorem which doesn't rely on making this ansatz. And they proved in general that these conditions, that rho matter is equal to 0 and curvature is positive on the boundary, implies that there is no wormhole solution. Okay, but that's not entirely the end of the story, because if you do have some non-zero rho matter, you can find solutions, and Marolf and Santos presented a bunch of examples. And another simple case is if you take k less than 0, so the spatial manifold is like a hyperbolic space or something like that, then you do find solutions. So actually, in this case, we can take A of rho is equal to cosh of rho. And that will solve this equation.
I have a question there.
Yeah.
I think I remember in Whitney Out or even in previous papers that this k greater than 0 condition was necessary for some stability reason. Isn't that correct? That they have an argument like this is related to the more precisely to the Yamabe constant on the boundary, and that there are very general arguments that tell you that this has to be always positive? Or am I mistaken? Or?
Well, I mean, it makes sense to consider the boundary theory on a negatively curved space.
Yeah.
The kind of thing that you can worry about in that case is that depending on the situation, you can have instability to nucleating branes. This is one of the kinds of things that can happen. And this was discussed further in the Modesen and Mao's paper, and also in the Marolf Santos paper. But I think that the nucleation of branes type of instability is sort of a separate question to whether the wormhole exists.
Right. Yeah. Well, yeah, but maybe you could say that then it's pathological. It's only in some pathological cases when the boundary theory is not really well defined or whatever. But
yeah.
Okay, I mean, it's anyway, when you add matter in the bulk, it's clear that the argument breaks down.
Yeah. You could think about that indeed, but the position, as you say, is not ultimately sustainable because there are solutions with matter, I think there also are solutions that should make sense with negative curvature. We have to think about the brane instability, but I think this problem should also make sense.
Okay.
But I think this result is really interesting because there's a no-go theorem in the simplest case that you would start with. The Whitney Out theorem doesn't mean that there's no Euclidean wormholes. We never need to think about them, but it does mean that they don't exist in the simplest setting where you would have thought, and that's an interesting point. Okay, so this is the end of the review of last time. Now we begin new material. Let me check first to see if there are any other questions about what we've discussed so far.
No, so you can keep going, I guess.
Okay, all right. So we're going to discuss the existence of these wormholes and the existence and non-existence of these wormholes and what they mean when they do exist in a simple toy theory of gravity, Chief-Teitelbaum gravity. So this is a two-dimensional theory of gravity, and there are two fields. There's the metric, G mu nu, and there's a scalar field called the dilaton. So we have the metric and the dilaton, and the action for the theory is the following action. We have this first term here, which is a topological invariant. This is the Euler characteristic if we add the appropriate boundary term, extrinsic curvature term. So this term doesn't contribute to the dynamics in any way. It just weights geometries according to their Euler characteristic. But you'll notice that this first term here that we wrote is it's kind of the analog of the Einstein-Hilbert action in 2 dimensions. It's this, again, the simplest term that you would write down, just R times root V, and it happens to be a topological invariant in 2 dimensions. So it doesn't give an interesting theory of gravity by itself, but it does weight different topologies. Okay, so then this other term is added to it in order to get a theory with some dynamics, a non-topological theory. We take R plus 2 and multiply it by our scalar field phi. So one thing that you can see from this is that if we look at the equations of motion that we get by varying with respect to phi, we're going to get a simple equation R plus 2 is equal to 0. So R is equal to -2. So we'll have negatively curved spaces as solutions to this theory. So JT gravity, it's a theory of basically rigid, negatively curved spaces in 2 dimensions, weighted according to their topology. And we're going to be thinking about these wormholes in the context of ADS-CFT, gauge gravity duality. And there's basically one element of the dictionary that we need to keep in mind, the dictionary relating boundary and bulk quantities in gauge gravity duality. So in this 2-dimensional theory, the most important entry in the dictionary is the following. If we have the boundary theory and we want to compute the thermal partition function, that is trace of e to the minus beta times h, where h is the boundary Hamiltonian. So boundary theory, you should think of some quantum mechanics system, like 0 + 1 dimensional quantum mechanics system. There's some Hamiltonian of the quantum mechanics. You can consider the partition function trace of e to the minus beta times h, where beta is the inverse temperature. And that thing is related in the bulk theory to a boundary condition for the gravity problem, where you put a circle, an asymptotic circle, and the circle has length beta over epsilon, so it depends on the inverse temperature. So the circle here, this asymptotic circle, has length beta over epsilon. And we also put a boundary condition for the dilaton. Dilaton we set equal to 1 over epsilon. And then we take the limit epsilon goes to 0. So this is sort of familiar holographic normalization. You impose asymptotic boundary conditions as a limit of a boundary condition with some very big boundary beta divided by epsilon with a value of phi that's 1 over epsilon. Then you take the limit epsilon goes to 0. Okay, so if we want to compute the partition function, we should put a big boundary, a big circular boundary out at infinity, and then we should just figure out what we're supposed to fill this in with in the bulk theory. So we put this big boundary there, and then we fill it in somehow with solutions to the Jakob-Teitelbaum gravity theory. So let's look at the basic black hole solution in this theory. That one looks like the following. We have ds squared is equal to d rho squared plus sinh squared rho d theta squared, and the dilaton is equal to some parameter times cos rho. And this is the geometrical part of this is just the hyperbolic plane written in polar coordinates. So here we have the hyperbolic plane. Here's rho equals 0. Here's rho equals infinity. And this is the basic solution of the Euclidean Jakob-Teitelbaum gravity theory. So this looks like a disk. It has the topology of a disk. And that's the appropriate topology for a 2-dimensional black hole in Euclidean signature. So what a black hole means, what a black hole solution means in Euclidean signature, it means that the Euclidean time direction is contractible in the bulk. And that's the fact that the Euclidean time direction is going around here, around this asymptotic boundary. And that is contractible in this disk geometry. Okay, so this is the Euclidean picture. And it's very useful to think about a continuation of this Lorentzian signature, where we start with this slice here. We declare that to be the t equals 0 slice, which is shared between the Euclidean and Lorentzian geometries. And then we continue that slice in Lorentzian time, not Euclidean time. And if we do that, we get the following geometry. Let me try to draw it. Okay, what do we get? Oops. We get this geometry, which can be written in these coordinates here. We have ds squared is equal to minus dt squared plus d rho squared minus sinh squared rho dt squared, and those give these coordinates for this portion of ADS2 space. sorry, the drawing's a little bit messy, but hopefully you have seen this diagram before, and you know what I'm trying to draw. So this is the Lorentzian signature, and the left is the Euclidean signature of the basic black hole solution in JT in Joukiffe-Tidal quantum gravity. And let me just draw once more the asymptotic boundary. On the left side, the asymptotic boundary, there's two separate asymptotic boundaries here and here. So we get a two-sided black hole, like we always do when we analytically continue at the Euclidean black hole into real time. We get a two-sided black hole connected by an Einstein-Rosen bridge. Okay. So here's what we're going to do. Here's what we're going to do in this JT gravity theory. We're going to recap in this setting the Whitney Out Theorem. So we're going to show that there's no classical solution that looks like this wormhole here when we don't have any matter. So there's no wormhole solution of this kind. Then we're going to try to evade that theorem in various different ways. We're going to try to get around it and find wormhole solutions that we can put to work in different ways. So one way will be to add some interaction between the two boundaries of the picture that we just drew. This leads to a really fascinating geometry called the eternal traversable wormhole, was discussed by Madasena and Chi. Then we'll try another thing. We'll try to stabilize the wormhole with gradient energy. And this is a simple example of the more complicated wormholes that are constructed by Marolf and Santos in higher dimensions. So that's a kind of a two-dimensional example that lets you understand the ingredients that allow Marolf and Santos to construct solutions also in higher dimensions. Then we'll remove the matter and find a solution called the double cone solution, which exploits a kind of a loophole in the in point 1. And finally, the last thing we'll do is we'll do the path integral without worrying about whether we find a classical solution or not. So this theory is simple enough that we don't need to confine ourselves to classical solutions. We can just try to do the quantum gravity path integral, regardless of whether there's a stationary point. And we'll see that we get we get an interesting answer. Okay, so that's the plan for the rest of today. Any questions about this or about the JT gravity setting?
No.
Okay.
So you can continue. I think this part we know because we discussed it a lot to prepare your lectures actually.
Okay.
And that explains, I think, why maybe there's no question, because it was already sort of discussed, and no, it's just a very nice review, but so you can continue.
Well, don't be afraid to ask questions, even if you've seen this before. Maybe there's something that puzzled you or something. So don't be afraid to ask questions. Okay, so let's show that no solution exists. No solution, no vacuum solution of a wormhole that looks like this exists. So a first step here is something I'm not going to do. It's simple enough, but we're not going to do it, which is to show that any solution to the Joukiffe-Tidal gravity theory has a U1 symmetry. So this is kind of an analog of Birkhoff's theorem, but in the JT gravity context. And it's easy to prove by using the equation that you get by varying the metric. But I'm not going to use that. We're just going to start by assuming that we have a wormhole with a U1 symmetry, and we'll show that there's no solution. So we're going to have kind of the same setting that we had before, where we have a rho coordinate parametrizing the distance along the wormhole. And then we have another coordinate. I'm going to call it y this time instead of theta, a y coordinate that goes around the circular direction. So the metric is ds squared is equal to, we're going to put some general function f of rho times dy squared plus another general function g of rho times d rho squared. And the dilaton will be some function of rho. So this has a U1 symmetry that corresponds to translations in Y. And actually, this is the most general form possible for a wormhole that connects these two asymptotic regions. Okay, so the action of JT gravity, ignoring the topological part, the part proportional to S naught, we just substitute in. So I'm going to put a 1/2 here to make it slightly cleaner. So this is the action of JT gravity. And if we substitute in with F and G, then we get the following: minus integral d rho minus phi times F prime over G. The prime is derivative with respect to rho, plus FG. So so this is the action of the JT gravity theory, and now let's vary it with respect to the F and G parameters. So we don't need to vary with respect to phi. Let's vary with respect to F and G. So the equation that we get by varying with respect to G, minus phi prime F prime plus F is equal to 0. And the equation that we get by varying with respect to F, minus phi double prime plus 1 is equal to 0. After setting G equals 1, which we can do by reparameterization. So we've written down the equation that we get by varying with respect to G. But after writing those equations, we have done a reparameterization of rho to set G equals 1. So we get these equations, and if we're trying to find a solution like this, phi has to be of order 1 over epsilon on both of the boundaries. So phi has to be very big on both of the boundaries. And therefore, phi prime has to be 0. I think I've forgotten a phi here. I've forgotten a phi here. Sorry for this. So phi has to be large on the two boundaries, and phi prime has to vanish somewhere in between. This is very similar to the argument that we made in the Whitney and Out case a moment ago. Phi prime has to be 0 somewhere in between. And at that point, where phi prime vanishes, phi double prime cannot also vanish. Because if phi prime and phi double prime vanish, then this second equation here will just say that phi is equal to 0. So at that point, phi cannot vanish. So if we look at this equation here, phi prime vanishes, phi does not vanish. That means that f has to be equal to 0. F has to be equal to 0 at that point. And what is f? F is the size of the wormhole in the y direction. So f is like the width of the wormhole. So that means that actually the solution we've constructed would have to look something like this. It has some 0 size in between. Like the geometry degenerates. So the only possible solution would be one like this, where the geometry, where the wormhole degenerates in the middle. And this would not be a real solution. It would not be a reliable solution. It could be maybe considered as a solution at the boundary of moduli space, but it's not an honest solution like the one that we sketched. So this is the application to JT gravity of the Whitney and Yao idea to prove that the solution doesn't exist. Okay. So we can understand a little bit better. We can try to interpret this, the fact that this solution doesn't exist, try to understand why it doesn't exist, by constructing constrained solutions where the length across the wormhole is fixed. So why that's helpful, we'll see in a second. So our plan is to construct the following situation. We want to find a wormhole solution like this, where we solve all the equations subject to the constraint that the total length across the wormhole. So the length L is the length across the wormhole, subject to the constraint that the total length across the wormhole is fixed. So I claim that there are solutions if we constrain the length across the wormhole, and we're going to try to interpret that fact and understand it. So first of all, how do we construct solutions where the length across the wormhole is fixed? Well, we can add a Lagrange multiplier for the length. So to add a Lagrange multiplier for the length, you just add to the action the length times some parameter. So we'll call the parameter m, and we'll add to the action here plus m times the length. The length across the wormhole is going to be the integral of square root of g d rho. So the length for this U1 symmetric wormhole is just an integral. The geodesic will be just in the rho direction, and the length of that thing will be m times the square root of g. And for the wormhole that asymptotes to asymptotic boundaries, that length will be infinite, but we can consider the regularized length, where we subtract a universal divergence coming from the asymptotic region of the wormhole. Okay, so we have this. I should have written it this way, m times length. So this is geometrical. And here, when we write it in terms of f and g, this is m times integral square root of g d rho. Okay, so how does this change the equations of motion? The second one, it doesn't change at all, because that one was the one we got by Verne with respect to f. But the first one, it changes by adding here f phi plus 1/2 m equals 0. Okay, so now let me make the sign so that m can be positive, and we can find a solution. If we now look at this equation and try to run the same argument, so we run the same argument, we say phi prime vanishes somewhere. Well, if phi prime vanishes somewhere, that's actually fine, because the other two terms can cancel each other if m is non-zero. So if the Lagrange multiplier that determines the length is non-zero, then we can have a solution. So, and we can try to understand the, that's the conclusion. Okay, I was unhappy about this sign, and I realized the problem is I forgot this minus sign here. So the sign is actually this one, and that gives us the equation that we had before. That sign is important because what is this term doing? This m times length term. If we add m times length to the action, that's like weighting configurations by e to the minus m times length. So it's favoring configurations where the length is shorter. So what this term that we've added to fix the length constraint does is it kind of provides a force that encourages the wormhole to be shorter. And that's the thing that gives us a solution. That's the thing that gives us a space solution. Okay.
So Douglas, sorry, a small question. So why was it that it would not be okay before you add this term with m? Why would it not be okay for phi to vanish at this middle position?
Yeah, it's because that's a good question. If phi vanishes and if phi vanishes at the same point that phi prime vanishes, then this equation here will imply that phi is just equal to 0. So if phi and phi prime vanish at the same point, then this equation says that the solution is just phi equals 0. And that will not be consistent with our boundary conditions, which require phi to be large, like 1 over epsilon at the two ends of the wormhole. So yeah, that's a natural, yeah, sorry.
So that excludes things like phi going like rho to the 4th power or something, or where at rho equals 0, several derivatives would vanish, but
right. So that that kind of function exists, but it can't solve this equation. So phi can't be any function we like, so we can't just write down phi equals rho to the 4th power because it has to satisfy this equation.
Okay, thanks.
Okay. Okay, but once we add the Lagrange multiplier term m times length, then we have no problem finding solutions. So we can understand this a little bit better. We can think about it as some kind of a spring, if you like. If we have a spring that is holding together the two boundaries, then we have a solution. And that kind of identifies for you what the problem with the wormhole was, why kind of gives you understanding of the Whitney Out result. The reason why the wormhole solution doesn't exist is because it wants to get longer. The wormhole has an instability. It has the action of the wormhole has an unstable direction. It favors longer and thinner wormholes. So it kind of wants to run away to a configuration that looks a little bit like what we drew. A wormhole that's very, very, very long and gets very, very, very thin in the middle. So and the endpoint of that kind of instability is an infinitely long wormhole that actually has a cusp. So it would be two infinite cusps. So an infinite cusp over here and an infinite cusp over here. And that is formally a solution. That's this kind of solution of the boundary moduli space that we found before. And if we include the m times L term, this spring, then it pulls the boundaries together and gives us a solution at a finite point in the moduli space of this cylinder. Okay, so we can try to make this a little more precise. There's a really nice formula, which is simple to derive. It's no harder than what we've done already, but I'm not going to do it now. There's a simple formula for the off-shell action of the wormhole as a function of the length, as a function of the constrained length. And the action of this configuration is the following: beta left plus beta right times the ADM energy as a function of the length plus m times L. So I'm not going to derive this formula, but I'm going to explain it. It's simple to derive, simple enough to derive by taking these equations here and plugging them back into the action. You plug these back into the action, and you can recognize some different terms as the ADM, as the ADM mass. So basically, after using these equations, the action becomes a total derivative, which reduces to the ADM energy. So what are beta left and beta right? Beta left and beta right are the parameters of the boundary circles, the lengths of the boundary circles. So the circle on the left has length beta left over epsilon and phi, so length and phi is equal to 1 over epsilon. So that's on the left side. On the right side, similarly, the size of the circle is beta right over epsilon at the point where phi is equal to 1 over epsilon. So those are the parameters beta left and beta right, and they are identified with the inverse temperatures of the thermal partition function that we're computing on the left and the right. Okay, so that's the first factor, beta left plus beta right. The second factor is the ADM energy. That's the energy of the solution as measured at infinity. And it's a function of L because this whole family of solutions is a function of L. And the last term here is the Lagrange multiplier term that we've added explicitly, m times the length. So this is the formula for the action. And we can see from this formula some of the properties that we've been discussing. So first of all, the energy this is another calculation which I'm not going to do, but is true. It's proportional to e to the minus the length across the wormhole. So the ADM energy of wormholes that are very long is small, and the ADM energy of short wormholes is high. So that means that if we remove the Lagrange multiplier term, so if we remove this term here, then you can see that by this action is not going to be stationary under variations with respect to L. This is the point that we just discussed before, that it has a runaway direction. L wants to get very large because the whole action is proportional to e to the minus L. So we can lower the action by making L larger, all the way to L goes to infinity. But once we add this term plus m times L, then there will be a stable minimum at some value of L that depends on n. Okay, but something that we're going to use later is that the off-shell action with no Lagrange multiplier term is beta left plus beta right times e to the minus L. So this is something very geometrical. The action, it's proportional to e to the minus the length across the wormhole. It's proportional to the sum of the sizes of the circles on the two sides, the left and the right side. Okay, and that formula by itself kind of explains why there is no solution without the Lagrange multiplier, but also you can see how there's a solution once we add a term m times L, or if we just constrain the length L to begin with. Okay, any questions about this?
Hello, hi,
Yeah.
Can you hear me?
Yes.
Hi, thank you. Just a quick question. I guess the fact that you have the ADM energy or mass that is just one when you have two boundary comes from the fact that phi is 1 over epsilon in both sides, but can you have a construction in which the left and right energy are different?
No. So the left and right energy are the same. So that's something that you can show using the equations of motion.
Okay.
The energy, ADM energy on the left and the right sides are equal. Yeah, even if the beta parameters on the left and the right side are different, the ADM energy is the same.
Okay, thank you.
Yeah, that's kind of a manifestation of like Gauss's law. If we have no no matter in the interior, then the ADM energy on the two sides should be the same. Okay. Okay, other questions about this? This formula here is really helpful. I find this formula really helpful for thinking about these wormholes, and we're going to use it repeatedly in the rest of today. And you might be annoyed that I didn't derive it for you, and that's true. But the derivation is not really hard. It just, you take this equation and plug it back into that action. So I didn't want to go through that, but it's straightforward to do. Okay, so we're going to use this formula now, and we're going to see how we can make wormhole solutions without this kind of artificial interference where we just constrain the length. So we saw a second ago using the Lagrange multiplier, you can find a solution if you just by hand constrain the length of the wormhole not to be large. But we want to do something a little bit more physical and try to understand cases where the wormhole solutions appear without putting that constraint in. So here's one really nice one. So this is, we're going to explain the eternal traversable wormhole of Maldacena and Chi, which was based on a earlier paper by Gao, Jafferis, and Wall. So, or it was, it used, I'm not, based on is too strong, but it was influenced by that paper. So the setting, let's forget about gravity for a second and explain the setting from the perspective of the boundary theory. So from the boundary theory, we imagine that we have two quantum mechanical systems, and they're in a, entangled state. And the two separate quantum mechanical systems in an entangled state, the thermal field double state, is described, sorry for scrolling back, is described by this solution. This Lorentzian signature solution of JT gravity, where the two red boundaries represent the two boundaries of these two quantum mechanical systems, and the entanglement is somehow related to the fact that we have a spatial connection between the two boundaries. A notable feature of this geometry is that it is not possible to send a signal from one boundary. Let me make this bigger so you can see it better. It's not possible to send a signal from one boundary to the other. If we send a signal here, it doesn't quite make it to the other boundary. So similarly, if we send a signal from here at the earliest possible time, t equals minus infinity, it doesn't quite make it to the other boundary. So this is t equals plus infinity, this is t equals minus infinity, and similarly on the right boundary. So this is this is a non-traversable wormhole. And that's the description, geometrical description of these two quantum systems to begin with in this entangled state, the one on the left and the one on the right. Okay, so what do we do next? What we do next is we add a wire, some kind of interaction between the two systems. So some kind of fairly weak interaction between the two systems, some explicit coupling between the two systems. And now, of course, you can see that it's going to be possible to send information from one to the other because it could travel through the wire. So we should expect that it's possible to send signals from one system to the other through the wire. But we're going to take the wire, this interaction between the two, to be something which is simple to describe, kind of using the individual degrees of freedom of the quantum mechanical system. So the simple degrees of freedom of the quantum mechanical system. In particular, we're going to take the Hamiltonian. Sorry, this is too big. I'm going to take the Hamiltonian to be the unperturbed left and right Hamiltonians. And then we're going to add, with a minus sign, some operator on the left times some corresponding operator on the right. So this is our new interaction Hamiltonian. It's going to involve a weak interaction parameterized by the coupling G between the left and the right system, just a multiple of an operator on the left and an operator on the right. And actually, to make this story precise, it's important to consider a sum of such terms where the sum runs from 1 up to k, where k could be large compared to 1, but it doesn't need to be large compared to any of the gravitational parameters. So k equals 100 would be good enough. And I'm going to suppress the parameter k in the remainder of the discussion just to make the formulas a little bit simpler. But if you want, you can keep in mind that we should really consider a sum of such terms. Okay, so this is our Hamiltonian. And we would like to understand what is the geometry that we get if we consider this setup. So one thing we can consider is we can consider the thermal partition function. So we can consider computing z equals trace e to the minus beta times h for the whole combined system, for the left system and the right system, and also their interaction. So what does that look like in gravity? How do we translate this problem to gravity, and can we have a wormhole that contributes? So, well, we use this dictionary, element of the dictionary that we described before. So we should have two boundaries, one for the left system and one for the right system. This one has length beta over epsilon. And this one over here also has length beta over epsilon. And there's some kind of interaction between the two boundaries, some wire that allows some interaction like this. O left times O right interaction, which I'm drawing with these dashed lines. So these are the boundary conditions for the gravity problem, is these two asymptotic circles and some interaction. We could imagine different kinds of geometries that could contribute, but the one that we're interested in is the possibility of a geometry like this, a wormhole that connects the two sides together. So to analyze this, what we can do is we can replace the interaction O left, O right by its expectation value O left, O right in the wormhole geometry. And the 2-point function of operators O left and O right on this wormhole geometry, Euclidean signature, will be of order e to the minus the conformal dimension of O times the length, regularized length across the wormhole. So this will be the 2-point function of the operators on the two boundaries will be proportional to e to the minus the distance between them with a parameter that is determined by the conformal dimension, just the conformal dimension, delta O. So that means that the whole action for our theory will be equal to I total will be the action of the wormhole without this term, and then plus minus, let me get the sign right, so minus G times O left, O right wormhole. So we have the action just of the wormhole, the gravitational part, and then we have the action coming from these from the fact that we've allowed this coupling between the two boundaries. And so what is this? So here we're going to use the formula that we had written before. So this is equal to beta left plus beta right times e to the minus L. So that's 2 beta e to the minus L. And this term here is minus G times e to the minus delta times L. Okay. So let's make a plot of this function. And we're going to assume that delta is less than 1. Like the plot of this function in the case where delta is less than 1. So the dimension of this operator is low. It's a fairly light operator. It has rather slowly decaying correlations. So let's imagine that G is small. And sorry, there's another term, beta here. The beta multiplying the second term is because this interaction happens at all times, and the integral over time gives a factor of beta, because the Euclidean time is compact with circumference beta. So the value here is like decreasing initially because it's mainly dominated by the first term, e to the minus L, if G is small. But for very large L, the second term is dominant because delta is less than 1, so it decays less slowly. So it's negative and approaching 0 out here. And indeed, a plot of this function looks something like this. So it's asymptotes to 0 from below, and it starts out positive. So it has some minimum at some value L star. So that means that after adding this interaction between the two sides, there is a minimum of the action and a stable classical solution, which looks something like what we do here, with some length between the wormholes. By the coupling formal dimension delta O. So that's a Euclidean wormhole, and we've kind of seen how the
looks like we've lost Douglas. We cannot hear you, Douglas, anymore. I don't know if you can hear me. It's like the connection has been lost. No, we still cannot hear you.
We see you, it seems like your mic is off.
Hi, can you hear me now?
Here you go. Yeah.
Okay. Not sure exactly what happened there. I think my internet cut out for a second.
It looked like an internet connection broke.
Do you see the screen? Is it sharing?
Yeah, it works again.
Okay. Okay. Sorry about that. What was roughly the last thing that I said before I disappeared? Do you know?
So you were discussing the existence that there were a minimum in this plot, and so that the wormhole would be relevant.
Okay.
That's all.
So there's a minimum for this plot, and we've kind of understood. So we understood before that the reason why there's no wormhole solution without any matter is that there's an instability towards the wormhole getting really long. And we had seen that just by hand constraining the length will give us a solution, but here we have a physical reason why we're kind of constraining the length. The physical reason is that we've added an interaction, O left, O right, that couples the two systems, and that is approximated by this two-point function. So the interaction between the two sides provides a kind of a force, a physically motivated force that holds the two ends of the wormhole together and gives us a solution. Okay, now this example is really nice because we can imagine the physics of the example is most interesting in Lorentzian signature. So we've discussed the Euclidean wormhole, but yeah, let me make a new page here so I can discuss the Lorentzian signature version. So if we take this wormhole that we drew here, it has a symmetry going around the time direction. So the Euclidean time is going around this direction. And we can continue that time to Lorentzian signature. And if we do so, we get the following geometry. We get a geometry like this with a time translation symmetry. So the U1 symmetry growing around the wormhole in Euclidean signature becomes a non-compact time translation symmetry in Lorentzian signature. And we have our two boundaries. So the left boundary is over here, and the right boundary is over here. So this represents like one of the quantum mechanical degrees of systems, and this represents the other quantum mechanical system. And the geometry that we found is a connected geometry. And you'll notice that now it's perfectly possible to send signals from one boundary to the other. So this goes on forever. So you have as long as you want to send a signal from one side and back again if you like. So these two systems can communicate with each other. They can communicate with each other through the wormhole. Now, you might not be surprised by that because we took these two quantum mechanical systems, as remember what our Hamiltonian is, we took these two quantum mechanical systems, H left plus H r, and we added an explicit interaction term, O left times O right. So certainly it is mathematically possible to send signals between the left system and the right system if you have a coupling term, O left times O right, in the Hamiltonian. The two systems are indeed coupled together, so it makes sense that you can send signals from one to the other. But the kind of cool thing here is that it looks like the way that you're supposed to be able to send signals is through the O field, through the O bulk field dual to the O operator, and kind of through these explicit interactions between the boundary points. So it looks like the way you're supposed to be able to send signals is like kind of directly through this O operator itself. And the bulk of gravity picture is kind of different. The gravity picture is that there's a wormhole that opens up and kind of you send signals through the space-time geometry. And this is a much simpler kind of a simpler way of sending signals. And it's kind of an emergent description of the coupling between the two systems through a space-time geometry instead of an explicit coupling through the boundary degrees of freedom. So it's obvious that you can send signals through this explicit kind of UV microscopic coupling between the two, but that through solving these gravity equations becomes an emergent, simple pattern of communication between the two boundaries. So this is the model Sandwich-Chi eternal traversable wormhole, and it's kind of a variant of the Gao-Jafferis-Wall traversable wormhole, which was the same setting, just with the coupling turned on for an instant of time rather than turned on for all time. Okay. Any questions about this wormhole? I don't remember folks being this shy last summer. I'm not sure.
But you're right. You're absolutely right.
If I'm going too slowly or too quickly.
Maybe it's very, very dark weather that we have here. You know, in January, we're all asleep. It's hibernation. No, I'm, I'm joking. But yeah, I encourage people to ask questions because I'm sure this last part is rather subtle. So I'm pretty sure some people may have questions. So, no.
Yeah, I don't want to put you on the spot, but please do feel free to interrupt and whatever. This is the main advantage to this thing. Like you can, I guess, read about these things in a much clearer presentation or elsewhere, but here we can have a discussion about it. So,
so everybody knows everything about this Maldacena Xi paper, probably.
Okay, so let's see how we're doing. So here's our little plan for this part of the talk. We've discussed this, and we've seen that we can stabilize the wormhole with this left-right interaction. The next thing I'll do just briefly is to discuss kind of a toy example of these Marov-Santos wormholes where you stabilize the wormhole with some gradient energy. So let's do that next. So let's imagine adding to our theory some matter. So we're now going to add some matter, and we'll add a complex scalar. Let's say a massless complex scalar with boundary conditions given by the following. So we have a wormhole. We're trying to find a wormhole solution. I'll draw this figure again for the 20th time. So we have a theta direction going around, and we're trying to make this massless scalar kind of wind once around each of the boundaries. So the boundary condition does not allow it to be constant. It has to wind like e to the I times theta as we're going around the boundaries. So let's see if we can find a wormhole solution in this case. Does this give us a compensating force that prevents the wormhole from getting really long? So what we're going to do is we're going to just try to evaluate the action root g d2x of the action of this scalar field. So I now contains this term. So let's try to evaluate this term. So the metric that we have is ds squared. So it's d rho squared plus b squared cos squared rho times d theta squared. So I can even put over 2 pi. Okay, so what is this? This is a hyperbolic wormhole, but it has a modulus. Modulus is the b parameter. So the b parameter is the circumference of the wormhole at the waist. So this is another parameterization. Instead of the length, we can use the b parameter. And these are related to each other by the following equation. We have beta times e to the beta equals e to the L over 2 times b. So beta is kind of the size of the wormhole at the big end, way over here. This has length beta over epsilon. And so you can see that beta and b are going to be linearly proportional to each other because the size at the big end is going to be proportional to the size at the waist. And the factor of proportionality is e to the length over 2 because the wormhole is growing exponentially in rho. So it's grown by distance e to the L over 2 in distance L over 2 in this direction. So that's the reason for this equation, beta equals e to the L over 2 times b. So since beta is fixed, we can either work with B, the waist of the wormhole in the middle, or L, the length across the wormhole. So either of these parameters are good parameterizations of this geometry. Okay, so let's see what the action of the scalar field is on this geometry. Well, the solution for the field, the classical solution for the scalar field with these boundary conditions is going to be constant, and we can work out its action. We can work out its action by computing this term, the derivative of f. So it's not varying in the rho direction, but we have root g is b times cosh rho, and then the gradient of the field f is going to be 1 over b squared cosh squared rho times f naught squared d rho. So this is the action. So this term comes from gradient of f squared. This term comes from root g. And if we evaluate this action, so this is going to be 1 over b times some convergent integral over rho, d rho over cosh rho times f naught squared. So sorry, this is a little bit messy, but you can see that the action is going to be proportional to 1 over b. And this 1 over b term in the action is going to forbid the wormhole from approaching a solution where b is small and the length is big. So again, this is going to give a term that wants the wormhole not to get too long and thin. It wants it to remain relatively short and relatively wide, reasonably large value of b. So, and the reason for this is fairly clear. We have a field with some gradient going around the circle, and it has to wind by 2 pi going around the circle. And if we make b too small, then it will have to wind around that thing very rapidly, and the gradient energy will make a big contribution to the action. So this gives us a term in the action that forbids the wormhole from getting too thin and too long. So again, one finds a solution by balancing these two terms against each other, the action from the wormhole and the action from this matter field. Okay, so in the paper by Moroff and Santos, they construct examples of these in higher dimensions and using somewhat more complicated fields. But the idea is basically the same, that you have some gradient energy which doesn't let the wormhole get too small in the middle, and that allows you to have a solution. Okay, so let's now discuss a case where you have a wormhole solution with no matter. So this sounds sort of paradoxical, but it's allowed by the Whitney Out theorem because we have complex boundary conditions. So this is what's called the double cone, and we'll discuss that now. We'll discuss it in JT gravity, although it's a more general solution. So let's go back to our formula that we've been using many times, the formula for the off-shell action of the wormhole with length L. So this is the formula. The action is proportional to beta left plus beta right times e to the minus L, where L is the length across the wormhole. So we've used this action several times before. Now we're going to do something that looks a little bit strange. We're going to try to remove this instability. So remember, what is the problem? The problem is that this formula is not stationary with respect to variations of L. The action can be reduced by making L large. Okay, so one thing we can do, the idea is to take beta left plus beta right to be 0. We take beta left plus beta right to be 0, and if we do that, then the action will be 0, and we won't have this instability. We'll have a moduli space of solutions with different values of L. So we can do that by taking beta left is equal to beta plus I times t. and beta right to be beta minus I times t, and then beta equals 0. So we start with these boundary conditions where beta left is equal to beta plus it, beta right is equal to beta minus it, and then in the end, we're going to take the parameter beta to 0. And you'll notice that as we do that, beta left and beta right are themselves not going to 0. They're going to plus or minus it. So the wormhole is not, the boundary circles are not becoming trivial. They're not becoming 0 size. They're just becoming imaginary length and complex conjugate to each other. So beta left plus beta right will vanish in this limit, so we can have a solution. Okay, and here this is indeed a solution. So let me try to explain why the solution exists. So we have two circles now, boundary circles as before, but they have lengths that are proportional to beta left and beta right, which are purely imaginary. So we have beta left is equal to it, beta right is equal to minus it. So these are boundary, the lengths of the boundary time circles in Euclidean signature. So a Euclidean signature length that is imaginary is like an ordinary real Lorentzian time. So it's like we have a solution that has real Lorentzian periodicity at the two sides. So the size of the circle is real in Lorentzian signature rather than real in Euclidean signature. So in principle, we start looking for something like a Euclidean wormhole, and we're looking for some kind of a special case of that where the boundary conditions have been analytically continued and really it has Lorentzian periodicity. So why do we have a solution in this case? Well, we can construct it by starting from the black hole solution. So this is a nicer drawing of the thing that I drew before, the reference black hole solution in JT gravity. I drew it like this thing, kind of messy at the beginning of the talk. So this is the black hole solution. So that's what's represented at the left here. And what we can do is we can take these two constant time surfaces, this constant time surface in red and this one in green. And we can periodically identify the solution under the time translation that takes us from one of those surfaces to the other. And if we do that, we'll end up with, so we started with a real solution in Lorentzian signature. And so after this identification, we're going to have two boundaries, which have the topology of two circles. And they're going to have length, which is real in Lorentzian signature. So it's like Euclidean length it on the left side and Euclidean length minus it on the right side. So a kind of a cartoon of what that geometry looks like is this thing on the right. It looks this like two cones kind of glued together at the tip. This is why it's called double cone. So the actual metric, let me draw the metric, is just the metric of the black holes here. So we have d rho squared minus sinh squared rho dt squared, and now t is identified with t plus some constant times the parameter t that we set the beta parameters equal to it and minus it. So this solution looks like it has a conical singularity at rho equals 0, where the two cones are glued together. But we should actually think of it with an I epsilon. So minus sinh squared rho plus I epsilon. And this smooths out the conical singularity to give a space that is smooth in the limit epsilon goes to 0. So the curvature is exactly equal to -2 everywhere. And it's actually a smooth geometry in the limit epsilon goes to 0 despite appearances. Okay, so this is a solution that exists actually for any black hole. We did this in JT gravity, but you can start with any black hole and just make a periodic identification by a time translation of the two-sided black hole and get a wormhole, a double cone wormhole associated to that black hole. So this is a kind of a universal wormhole geometry that exists for any black hole, so it should have some kind of universal explanation. And we can try to explain that. So what are we computing? So we can go back to this dictionary we've been using, that a computation of trace of e to the minus beta h is related in the boundary theory, it's related in the bulk theory to a boundary condition of a circle of length beta. So we now have two circles, one of length beta plus it and one of length beta minus it. So that corresponds to, in the boundary theory, to two partition functions, two thermal partition functions analytically continued to inverse temperature beta plus it and beta minus it. So in terms of the microscopic description of the boundary theory, in terms of the energies, that quantity is given by this expression here. It's a double sum over energy Em and En of e to the minus beta times e to the minus beta times the sum of the energies, and then e to the it times the difference of energies. And we're supposed to sum this over all the energies of the boundary theory. So this is the quantity that corresponds in the boundary theory to the bulk boundary conditions we've been discussing, where this wormhole solution exists. Okay. And this is a quantity that's known in the literature in quantum chaos as the spectral form factor. It's a kind of interesting diagnostic of the spectrum of energy levels. If you look at it, it's kind of like a Fourier transform in the difference parameter of the energy levels of 2 Em minus En. Okay, and what the spectral form factor does is it encodes a type of correlation among the energy levels, which is expected to be universal in quantum chaotic systems. And you might have heard that in quantum chaotic systems, the energy levels have interesting statistics, kind of like that of a random matrix. And the most famous example of that is that the distribution of spacings between energy levels in a quantum chaotic system has this Wigner-Dyson distribution, where something like this, the distribution of spacings is 0 if the energy levels are right on top of each other, and it kind of favors the energies being a particular distance apart from each other. That's one example of spectral statistics that are expected in quantum chaotic systems, but there's another one which is a little bit more subtle. It's a type of long-range anti-correlation between energy levels. So it's not between neighboring energy levels, it's energy levels that are kind of far apart from each other in the spectrum of energies of the system. And there's a weak kind of power law anti-correlation between those energies. So if I know I have an energy here, then it's a little bit, then all the other energies are kind of repelled from that one a little bit with a rather mild power law decaying behavior, 1 over delta E squared. And that power law gets picked up in this spectral form factor, in this Fourier transform, as this this ramp region here. So let me try to draw it in different colors so you can see. So this ramp region here, this linear growth of this function is associated to the repulsion, this power law suppressed repulsion of energy eigenvalues. And this is expected to be a universal feature of quantum chaotic systems. And this ramp has a long history in the literature in quantum chaos, semi-classical quantum chaos. So you'll notice that what is being plotted in this graph, first of all. So this is the spectral form factor as the y-axis, and time is the x-axis, and it's a log-log plot. And you'll notice that this red curve is extremely erratic. And that's the erratic curve that you expect to get for a single quantum mechanical system. This is actual numerical data from the SYK model. The black curve is an average over many realizations of that quantum system, and it's much smoother. And in the limit where you average over an infinite number of different systems, you get a smooth curve that contains this linearly growing ramp here. Okay, so the claim is that that ramp, that linearly growing ramp, is explained by this solution. So it's explained by this solution And the universality of that ramp in quantum chaotic systems is connected to the fact that this double cone solution exists for any black hole. Black holes are expected to represent quantum chaotic systems. So what we can do is we can explain, well, we can explain the fact that it's linearly growing in time. It's growing in time with proportional to t. That's just because when we construct this solution, we have to say where we set the origin of coordinates t left is equals 0 on the left boundary, and we have to say where we set the origin of coordinates t right equals 0 on the right boundary. And there's a zero mode, which corresponds to leaving the geometry exactly the same, but moving the point which we declare to be t right equals 0 on the right boundary. You might have thought we have two zero modes, moving the left one and the right one independently, but if we move both of them, then because of the symmetry of the geometry, we haven't actually done anything. So moving the two of them together is a gauge transformation, but moving them separately is not. So if we fix t left equals 0, then we can move t right equals 0 anywhere on the boundary. And so it's a zero mode, and it's a compact zero mode with size t, just the size of the boundary itself. So that means that the contribution of this geometry will be proportional to t, proportional to capital T. So we have an integral over t dtr from 0 to t is equal to t. And this factor makes the whole contribution of this double cone proportional to t, and can explain this ramp part of the spectral form factor. Okay, so there are some puzzles associated to this that we'll discuss more on Thursday. Okay, so let me just discuss the last thing. I guess my numbering is off somehow, but we've completed these things, and now let me just do one last thing, which is to do the path integral without stabilization. So suppose you want to compute this wormhole, and we don't worry for the moment about whether there's a classical solution. We just try to do the quantum path integral. Okay, so there are different ways of doing this path integral in JT gravity, but one simple way is the following. We can take this wormhole and we can cut it in half in the middle at the waist of the wormhole, where we have a circle of length b, the minimum size. And then we can construct the whole geometry by gluing together the two of them and integrating over the length where we've glued them together. So that means that we have an expression for the whole wormhole as an integral with some measure factor b db. That factor of b represents the freedom to twist one of these things relative to the other. It's exactly the same factor of t that we had discussed a second ago. So the measure factor of b arises just from the twist of one side relative to the other. So we have integral b db times these two factors, which are the path integrals for these two separate trumpets. So these things are called trumpet geometries. And the path integral for those two separate things factorizes into these two expressions. Don't worry too much about these expressions. The main thing to notice is that they're proportional to e to the minus b squared over beta. So this is the instability that we've been discussing many times, that the wormhole prefers b to be small. It wants the circle to be small, it wants the wormhole to be large. And that's just the fact that this integral here over b has no saddle point. It has no saddle point. Well, it formally has a saddle point at b equals 0, but that's a boundary of the moduli space where the wormhole is infinitely long and thin. But we can just do the integral. We can just do the integral over b, and we get this answer here. I think I have a typo. I suspect these 2 pi's here should probably be 4 pi's. But I can't remember exactly if that should be 2 pi or 4 pi. Anyhow, you get this expression here, square root of beta left, beta right, divided by 2 pi times beta left plus beta right. So that's what you get by just doing the path integral exactly over these geometries. And I just want to make one comment, two comments about this. One comment is that we can set beta left equals beta plus IT. Beta right is equal to beta minus IT. And we get, and if we take T large, we get something which is like T divided by 4 pi beta. And this is this ramp behavior that we discussed a moment ago. And the large time behavior of this thing is controlled by the double cone solution. So this kind of confirms the slightly imprecise discussion we had a moment ago of this classical solution when in this double cone limit. And the second comment is that this is exactly the answer for the connected correlator e to the minus beta trace e to the minus beta 1 beta left trace e to the minus beta right in an integral over Hermitian matrices H. So this function that we got here is exactly the function that you get in an integral over Hermitian matrices H. And that's actually part of a larger story that JT gravity is exactly dual to a matrix integral. And the wormholes encode the correlation between in the ensemble of different matrices. But we're not going to discuss that more. I just want to mention it as one thing, something related to this exact integral over these wormholes. Okay, so that's it for today. On Thursday, we're going to discuss this factorization puzzle a little bit more, and what can happen to the wormholes to restore the factorization, and to try to restore these kind of erratic wiggles in this graph. Okay, thanks for your attention.
Well, okay. First, thank you very much. I think it was a very, very, very clear lecture. Maybe that's why, we don't have questions so much. I have one, but so please, questions. I mean, we have plenty of time for questions. And
maybe I can start. So you've used JT gravity, so two-dimensional model. I was wondering if you have a sense to what extent this is a good model for what you expect to happen in higher dimensions. And I guess I'm asking from the point of view of the islands, etc., where these space-time wormholes have also played a role. To derive these formulas, there's been some debates on the extent to which these lower dimensional models should or should not be good models for higher dimensional gravity with massless gravitons, etc. So I was wondering if you could comment a bit on that.
Yeah, I can comment on that a bit. So we discussed various different. So let me try to discuss which of these things are expected to generalize to higher dimensions. So first of all, this result does generalize to higher dimensions. This is the Whitney Out theorem. This thing here, it sort of generalizes to higher dimensions because you can have eternal traversable wormholes with near extremal black holes in higher dimensions. So basically using the JT analysis, because JT gravity is an accurate description of near extremal black holes, including in higher dimensions. So the reason you need that is you need the near extremal condition so that the tendency of the wormhole to get long and thin is weak. It needs to be weak enough that it can be compensated with some matter fields, and it becomes weak in the near extremal limit. So that's why that one, it generalizes in that sense. Yeah, this third thing, well, it's been discussed in the paper by Marolf and Santos. They have many examples in higher dimensions. The double cone solution exists for any black hole, in particular for higher dimensional black holes. And the thing that does not generalize is this fifth one, because we don't know how to do the path integral in higher dimensional gravity. So we're kind of confined to classical solutions. There's kind of an exception to this, which is in three-dimensional gravity, but I think that's not really, well, there's a paper by Kotler and Jensen doing the path integral exactly in three-dimensional gravity, but maybe that's more similar to JT than it is to higher dimensions because we don't have dynamical gravitons in that case also. So some of these things generalize, most of them generalize, some of them do not. So you asked about the replica wormholes for the entropy. I didn't discuss that in my lectures here because, well, one reason is that I didn't have time. Another reason is that there's plenty of nice lectures on this. I give, well, there's plenty of nice lectures that you can find on this subject. And this should have no trouble generalizing also to higher dimensions. It becomes more technically difficult to find the solutions. In fact, it's already difficult in 2 dimensions. Nobody has found analytical solutions for the replica wormholes with non-zero Renyi index. Even in JT gravity, it's just analytically difficult problem. But the limit n goes to 1 of that replica computation is just the quantum extremal surface, and that one is fine in higher dimensions. It doesn't require JT gravity.
I thought there were some papers by Karch, Randall, Suvrat Raju, and others who, I have studied them in detail, but they seem to be claiming that at least some of the features would not extend, and or you would only find islands in situations where the graviton is massive and things like that.
There's some discussion about the asymptotically flat case, and there's some discussion also about the case with the, in the case where you have some explicit coupling to a bath, then I think those authors don't think that there should be any problem also. I think this is a case where they would say the graviton is massive, where you have some
right.
Yeah. Whether you use that terminology or not, I guess it's up to you.
But I guess one question is, would you expect, like in, for instance, an asymptotically flat geometry with real-world black holes, that the basic phenomenon of islands, etc., would still hold, or is it an artifact of either the low-dimensional models or models with massive gravitons and things like that?
Well, no, I do expect it. I expect it also in an asymptotically flat case. I guess you have to do, depending on exactly what computation you're doing, you'll have to set it up so that the black hole, contributes to begin with. So in asymptotically flat space, even if you compute the thermal partition function, you should put the black hole in a box or something in order to get a reasonable answer. And I guess you would have some similar situation here, but I don't expect any problem in the replica wormhole analysis. Basically, because the considerations are, I don't think should depend too much on the asymptotics. It's possible that the authors of the paper that you mentioned would not agree with that statement, and I'm not sure what to say about that.
Okay, great, thanks.
So any other question? Otherwise, I can ask a question that probably is going to anticipate the discussion on Thursday. So it looks like really that these 2-dimensional models are not dual to quantum mechanical systems, as you say, just because of this factorization problem and blah, blah. So it's a very strange, unexpected thing in holography, even if it's in 2 dimensions, that quantum gravity doesn't look like a genuine quantum mechanical system after all.
Yes.
So do you think the reason is that maybe we've missed something with these toy 2-dimensional models, that maybe the analysis that's been done, it's not like been pushed at the level of full mathematical rigor, like some people have done now for Liouville gravity, for example. So do you think there's the possibility that those 2D models could be cured in some way on their own, or that it's not going to be possible, and then, you know, then it's the other way, and there's really no quantum mechanics for this 2D case?
Well, let's see. I think it might depend a little bit on what you mean. So the two-dimensional models by themselves are well defined. So at least to all orders in the genus expansion, JT gravity is perfectly well defined, and the matrix integral that it's dual to is also perfectly well defined. So those things are rigorous mathematics. There's a sort of a step in the non-perturbative completion of that asymptotic sum over genus that is not unique, and one makes a choice in completing it with a particular contour in the matrix integral. But in supersymmetric cases, there's really less ambiguity in what contour to take. So I don't think that ambiguity is really meaningful. So I would say that up to the subtlety, which I don't think is really significant, the JT gravity theory and the matrix integral are both rigorously defined and dual to each other. So it's not that we're not analyzing the gravity theory correctly. So we're analyzing it correctly, and it is really dual to a matrix integral. Now, the answer to your question could still be yes, because basically we could be missing something that we were supposed to add. Like we weren't really just supposed to study JT gravity by itself. So JT gravity by itself is dual to matrix integral, but maybe you add some other stuff to the bulk theory and you get something more interesting. And that's possible. And I think certainly to the extent that it's a model for higher dimensional gravity theories, which we, at least in some cases, do expect to be dual to a specific quantum system, then there must be stuff that you're supposed to add, additional things that you're supposed to add to the gravity theory that kind of fix this factorization problem. Yeah, that's something that we'll discuss on Thursday. But it's not, you know, on this Thursday I'll discuss kind of one proposal for this in a unfortunately in another simple toy model, because that's kind of the state of the art. But different people have different ideas on this, and it's not a question of settled science for sure.
All right. So we look forward to the first day's lectures for more information on this. So any other question? No? All right, so I think we can probably close today's lecture and thank Douglas again for the very, very clear exposition that we had. So.
Okay, yeah, thanks. See you.